All right, so last time we saw how to formulate GR in terms of an action principle. And we saw that, well, apart from the boundary terms we had to worry about, to write down an action is pretty simple. You just say that, well, the action has to be a scalar. It has to involve, the metric and its derivatives. Therefore, it has to involve the Ricci scalar. So to write down the action was pretty simple. To vary the action to get the field equations, well, that required quite a bit of work. And it's in doing this work that we recognized that in order to have a well-defined action for a well-defined variational principle, we had to include boundary terms into our action principle. So anyway, now I want to take the next step, which is to, start from the action we were given last time and construct a Hamiltonian formulation from this. And it turns out that to get the Hamiltonian out requires quite a bit of work. So to get the Hamiltonian from the action requires a lot of, not hard work, but just very detailed work where you keep track of everything, including everything that's going on the boundary. So we'll spend quite a bit of time on that today. To get from the Hamiltonian to Hamilton's equations, that would be an alternative formulation of the field equations in the same way that Hamilton's equations are an alternative way of writing out, the Euler-Lagrange equations in mechanics. I go through that in the book, but I will never do that in class. It's just horrible. It's just, too long. It's just, again, it's straightforward. You have to just, go through it, but it's not something I would dare to do in class. It's just, way too long. So I won't do that, but the interest here is not really in getting the Hamilton version of the field equations. That's something that does have some interest, for example, in formulating, for example, equations for numerical relativity. But the interest in getting the Hamiltonian, as I told you, is that it gives us a means to formally define what we might mean by the total energy of a space-time, or its total angular momentum, or its total linear momentum. So that's really, the interest is really in the Hamiltonian itself. So today is all about the Hamiltonian formulation. And just the road from writing down the action, which we know, to extracting the Hamiltonian, requires quite a bit of work. And I think that will probably occupy us for probably the whole day today. I hope I can finish it. Probably I will finish it, but it's going to be packed. And again, it's not that it's hard. It's just that there's a lot to keep track of, and we're going to have to, be patient and keep track of everything. So if we just go back to mechanics, just for getting us started thinking about this, when we go from a Lagrangian to a Hamiltonian in mechanics, well, we know that the first thing to do is to obtain the canonical momentum associated with each of the generalized coordinates that we have in our system. So if we have a Lagrangian that depends on coordinates q and velocities q dot, then the first step in constructing the Hamiltonian is to compute P, which is defined to be the derivative of the Lagrangian with respect to q dot. So the first step is to get the canonical momenta. And once you have the canonical momenta, well, to get the Hamiltonian is pretty simple. You just take P multiplied by q dot. Of course, you re-express everything in terms of P. You subtract the Lagrangian, and that's your Hamiltonian. And the Hamiltonian, of course, has the interpretation of being the total energy of the system. And then you can go ahead and write down Hamilton's equations for P and Q, and you've succeeded in writing the F equals ma in a form that involves a coupled set of first-order differential equations. It's very convenient for doing all sorts of things. And but in our context, the interest in this is not really to get the Hamilton equations, as I said before. It's really to get the Hamiltonian itself. So what is the Hamiltonian? First of all, for a field theory, and second of all, when the field theory is GR itself. So the procedure here is very simple, and the whole starting point is to take a derivative of your Lagrangian with respect to q dot. So now if we were going to do this for a field theory, we would have to think a little bit harder, and in particular think about, well, what do we mean by q dot in the context of a field theory? So first, let's think about doing this in flat space-time. For a field theory in flat space-time. Well, for field theory in flat space-time, well, the procedure is very analogous. You're given a Lagrangian density that will depend on your field and its derivatives. And from that, you're supposed to define a canonical momentum associated with your field. And the analogous operation here, it's usually called pi in the context of field theory. The canonical momentum associated with psi is pi. And pi is defined to be the partial derivative of your Lagrangian density with respect to the time derivative of your field. And as soon as you do that, of course, you get rid of the Lorentz invariance. You sort of put Lorentz invariance on the side, and you say, I'm going to be working in some specific Lorentz frame, and the time coordinate that I'm using here to define this time derivative is going to be the time associated with one very specific frame. So basically, the beautiful Lorentz invariance that you have at the level of the Lagrangian, you get rid of. And when you work in terms of the Hamiltonian, you make that choice of getting rid of manifest Lorentz invariance. Of course, Lorentz invariance is still built in. But by selecting a time derivative, that means that you've selected a Lorentz frame. And the whole construction then is going to be restricted to that choice of Lorentz frame. Of course, you can switch frames. You can do all of these things. You still have implicit Lorentz invariance in all of this because your theory started out with the Lorentz invariant action principle. But the point is that at the level of the Hamiltonian, this manifest Lorentz invariant is lost. You've made that choice, and you just have to live with that. Once you've defined this, once you've defined the canonical momentum, then the Hamiltonian density for your field is going to be, the directly analogous thing, which is you take pi, you multiply that by your time derivative of your field, you re-express everything in terms of pi, you subtract the Lagrangian density, and that is something that if you integrate over all space, you get something that obviously has the interpretation of the total energy for the field. This, by the way, would basically agree with what you would compute, in terms of the energy momentum tensor of your field configuration, of your field theory. That would correspond to the energy density of your field. And if you integrate the energy density in your field, you get the total energy. So in a field theory, the Hamiltonian has the interpretation of the total field energy. The really important point here is that whereas when you work at the level of the Lagrangian, you retain manifest Lorentz invariance. At the level of the Hamiltonian, you've made the choice to get rid of this, and you work in a very specific Lorentz frame. That defines the time derivative, and that defines, of course, what you mean by the spatial integration. You take, a slice t equal constant in Minkowski spacetime, and that's how you define your Hamiltonian. If we're going to do this in curved spacetime, well, presumably we want to be a bit more sophisticated than this. We could always choose to work in a given coordinate system and define the time coordinate, the time derivative of our field in terms of that specific coordinate system. But not only would we give up on implicit Lorentz invariance, manifest Lorentz invariance, we would also give up doing this on general covariance. We would give up the freedom of using any coordinate system we want. And that's something that would be too hard to, a price that would be too hard to pay. When we're going to generalize this in curved spacetime, we can do it in a way that still respects the spirit of the Hamiltonian construction, but preserve the fact that we would like to do this in a way that's still, generally covariant and all of that. So let me explain how it's done, but I don't think you'll be shocked by how we choose to do this in curved spacetime. So now we'll do a field theory in curved spacetime. And we're just going to import some of the ideas without necessarily importing all of the technical aspects of those ideas. The main idea of doing Hamiltonian field theory in flat spacetime was that, well, we were really foliating Minkowski spacetime in terms of a stack of t equal constant surfaces. So the essential point here is that we were thinking in flat spacetime in terms of a whole stack of t equal constant surfaces. This would be t equals t naught. This would be t equals t1, t equals t2. And by taking a time derivative, what we really thought about when we were doing this is considering how the field changes as you move up from one hypersurface to another. So, so the time derivative was really, in more sophisticated way of thinking about it, basically a comparison between the field configuration on this slice with respect to the field configuration on the next slice and the next one and so on. And by time derivative, we really meant what happens as you move up the foliation from one slice to another. Of course, in Minkowski spacetime, there's a preferred way of doing this. We take each slice to be t equal constant. We take each slice to be flat. But in a curved spacetime situation, well, bottom line is that we still want to do something like that to continue with the Hamiltonian formulation, but we don't want to do it in a way that's too rigid. We don't want to do it in a way that's tied to a specific coordinate system. We want to do it in a way that retains a good deal of the general covariance that we had before. But we still want to introduce this idea of a foliation of spacetime into a whole stack of space-like surfaces. So we're going to do that. That's going to be the essential input into the Hamiltonian formulation of a field theory in curved spacetime. But we don't want to rigidly specify what the foliation will be. We're going to make it what we want it to make, what we want it to be. Basically, we just say we're going to foliate spacetime with arbitrary space-like surfaces. So the foliation is absolutely important. So we will slice up spacetime in terms of space-like hypersurfaces. So we will introduce a 3+1 decomposition of spacetime. So the foliation idea is absolutely essential, but we can do it in a way that's much more sophisticated than this by basically selecting our space-like hypersurfaces in any way we wish. Give it any curvature, give it any shape we want. The only requirement, and it's an important one, is that this defines a proper foliation, which means that our surfaces will not be intersecting. They cannot cross each other. They have to stack up like this, very nicely without crossing. Yep.
Does it have to be a space-like hypersurface? Could you, let's say, foliate it in a null direction?
You can, yes.
So slices would be null.
Yeah. So you can. So there are Hamiltonian formulations based on null surfaces. They're much more sophisticated than what I'm doing here, because if you choose to do this, well, first of all, it's not enough to do it with one set of null surfaces. You have to do it with two intersecting null surfaces to define a good foliation. And if you choose to do that, basically now you choose to incorporate 2 times. You have a 2-time Hamiltonian as opposed to a 1-time Hamiltonian. And you have to deal with all the subtleties of the null hypersurfaces. So it's just much more involved. It can be done, but it's outside of what I want to do here. And it's a bit unusual. I don't think it's found a lot of very good applications in the literature. I mean, there is literature on this stuff, but I think it's a sort of narrow, marginal literature. I should always be careful what I say, because I know I'm being taped and somebody will object at some point to those statements. But as far as I'm aware, I don't think that a null Hamiltonian formulation has found a lot of powerful applications. So we're going to have a bunch of space-like hypersurfaces like this. I'm going to call them, sigma. I could call this one sigma 0, sigma 1, sigma 2, sigma 3. We have a whole bunch of them. And what I'm going to be meaning, of course, when I consider taking a time derivative of a field, will be obviously a derivative that will compare a field configuration on this surface to a field configuration on the next surface. So I will be considering essentially normal derivatives as a substitute, as a good geometrical substitute for what I meant over here by a time derivative. So the analog to what we had in flat spacetime will be the normal derivative of the field on each surface. And the canonical momentum is going to be defined in terms of those normal derivatives. We're going to make this a little bit more sophisticated. I'll introduce a whole lot more structure to it to make this more convenient. But the ideas are essentially here. So the canonical momentum will be defined in terms of that. The Hamiltonian density is going to be defined on each hypersurface. The Hamiltonian is something that will involve integration on each hypersurface. And the Hamiltonian is going to be basically a functional of a field configuration and its momentum, canonical momentum on each hypersurface. And from that Hamiltonian structure, you can get eventually Hamilton equations that will tell you how things evolve, how the field evolves from one hypersurface to the next, and how the momentum evolves from one hypersurface to the next. And the structure of Hamilton's equations will be saying that, well, this is equal to momentum, and then there's going to be an analogous equation that tells us what the normal derivative of the momentum is in terms of everything else. That would be the structure of Hamilton's equations coming out from a formulation like this. So those are really the ideas. Those are the essential points. The rest is just, okay, starting here and putting some structure on top of this so that we can do this in a very convenient way, in a way that ultimately retains the full general covariance of the theory, but still, introduces the stacking, this foliation as the really essential construction behind the Hamiltonian formulation. Okay, so what I'm going to do now is to just get going with this and start introducing all of these things that we're going to be needing, and the whole thing is basically based on this. It's a 3+1 decomposition of spacetime into a whole stack of hypersurfaces. So I'm going to come back to the scalar field theory in a second, but before I sort of turn this into something a bit more convenient to work with, I need to introduce these additional elements, and that's the purpose of the 3+1 decomposition. So any questions before I get going with this? Okay, so keep in mind that the basic ideas have already been covered. The rest is just the technical details that we want to put in to make our lives a bit easier. Okay, so I'll just keep this here so we can refer to that from time to time. So let's talk about the 3+1 decomposition. So I'll go back to those hypersurfaces. So basically, we just pick them arbitrarily. So we choose what we want to foliate spacetime with. And instead of calling them sigma naught, sigma 1, sigma 2, I'll just give them the generic label sigma t. And I'll be introducing a time function that will tell us how the spacetime has been foliated. So the starting point of the 3+1 decomposition is to introduce a time function. It's a field, it's a scalar field that we can express in terms of the spacetime coordinates, such that t is equal to a constant on each sigma t. So this would be the surface t equals t naught. This would be the surface t equals t1, t2, t3, and so on. So this function t, I call it t now because it really represents a time. We have a monotonic increase of time as we move up the foliation like this. So it's a good way of defining a time function. It's a good way of representing time in our spacetime. It may not agree with our 0th coordinate, so it may not be the actual time coordinate that we may have selected to define our spacetime coordinates. But it's a more meaningful time function because it's actually tied to the foliation that we were given, so that we have selected for ourselves. And essentially, that function over here, I used to call it phi in the context of hypersurfaces. So it plays exactly the same role as phi played before. Before, we used to represent a hypersurface by saying that phi is equal to 0. While the 0 is unimportant, we represent a hypersurface by saying that a scalar function of the coordinates happens to be a constant on the hypersurface, And now we have a whole stack, so we have a whole bunch of different constants that describe each hypersurface in the foliation. So that's the starting point of the 3+1 decomposition. At some point, I may choose to use this as an actual time coordinate in my space-time. I have the freedom to do that, but I also have the freedom not to do that. I can stick with whatever coordinate system was selected to begin with. So I retain general covariance through the arbitrary use of the underlying coordinate system. This is just to be thought of as a scalar field in my space-time. So, there's some fine print that this guy has to satisfy. It has to be a single-valued function. It has to be unambiguous. It has to lead to a bunch of non-intersecting surfaces. So you can either pick this function, and that will give you the foliation, or you can pick a foliation and try to construct a function that that's compatible with it. So whatever requirements we made on this, of course, have to be reflected in the choice of this mathematical function. Okay, the normal to each hypersurface is going to be up to a normalization, is going to be proportional to the gradient of that time function with respect to the space-time coordinates. So that's something we're used to. And well, I'll say something more about the constant of proportionality in just a second, in just a few minutes. So this doesn't have to be normalized, but of course this vector here has to be normalized. So the constant in front, of course, will come from the normalization condition. N, of course, is normalized in the sense of being -1. The epsilon for this n is negative. Okay. The next step in the construction is to lay down a coordinate system on each hypersurface. So that's something we're used to. We were used to, we were used to be dealing with a single hypersurface where we decide, okay, we're going to put a grid on it that may or may not be simply related to the grid we have in the underlying space-time. So on each hypersurface, I have the freedom of setting up a coordinate system, and I'll call it in the usual notation, I'll call this YA, the 3 intrinsic coordinates that I would use on each hypersurface. And, a priori, I don't have to link the coordinate systems from one hypersurface to the other one. I could do it independently here. I could do it independently here. I could do it independently here. I could choose, Cartesian coordinates here. I could use spherical polar coordinates here, and make another choice over here. Of course, that would complicate things, for no good reason. So the first thing I'll do, the next thing that I'll do is to say, well, I really want to introduce a relationship between the coordinates that I put here with the coordinates that I put there and the coordinates that I put down here. And the way to achieve this relationship, the way to put some rigidity into this construction is to, in addition to the hypersurfaces, to introduce a congruence of curves in the space-time that will be intersecting my, my space-like surfaces. So let's pick, so let's just draw a congruence of curves. One curve might look like this, another one might look like that. It has to be a proper congruence, so we still have all the requirements that those will be non-intersecting curves. But here, I don't make the requirement that they have to be geodesics, and I don't make the requirement that they have to be orthogonal to each surface. So they're really arbitrary curves in the same way that the foliation itself was completely arbitrary. There's no requirement that that they have to be geodesics, and there's no requirement that the crossing has to be orthogonal. I guess it's irresistible that when you draw it, you want to draw it sort of orthogonal, but here you can see that it's not orthogonal. So keep that in mind. So we have a congruence of curves. I always call my curves gamma, so we have a whole bunch of gamma curves here. And their role is to basically link the coordinates that I set up here to the coordinates that I set up here and here and here. So basically, those are curves YA equal constant. I insist that those curves will carry the spatial coordinates with them. So if I imagine setting up a coordinate system on this first hypersurface, then at this point I will have, you know, a triplet of numbers ya. At this point I will have another triplet, and I will have another triplet here. And basically the point is that I will follow the curves upward, and whatever ya triplet I had here, I will find it's here also. I will adopt it here also. I will adopt it here also, and so on and so forth. So that construction, so if I'm given the stack of hypersurfaces and the congruence of curves, that means that I can set up a grid once and for all on one hypersurface, and I just let the curves carry the grid along with it. Then I have a grid on all the hypersurfaces. So the requirement is that here ya is constant on all of those curves. And with that, I have a nice rigid construction. Of course, I still have a lot of arbitrariness here. I have total arbitrariness in which congruence I will be selecting. So the network of curves is completely arbitrary. How I set up my grid to begin with is completely arbitrary. So in the end, I do have, you know, a complete freedom in how I want to set up my coordinates. It's just that now I have some structure that tells me how it's all tied together. Another view on this is to say, well, I can set up a grid here, I can set up another grid here, and another grid up here. And so long as the grids are not vastly different from one another, so long as they sort of vaguely look Cartesian, for example, I can always relate points on the grid by connecting the dots and linking them with curves like this. That's another view on this. So I prefer the other view, which is to say that you set the grid once and for all on one hypersurface, and then you let the curve carry the grid along with them, and so that now you have the grid on each hypersurface once and for all. Of course, we're all doing this, you know, in a local patch, in a finite domain V of the spacetime. We don't have to do anything like this globally. Globally, there might be some difficulties in making sure that, you know, you never get intersections or anything like that. So we're happy to just do it in a finite patch, and we might, you know, cover the whole spacetime with different patches if we had to. All right. So with that, we pretty much have everything we need in the construction, and the rest is just working out the mathematical consequences of all of this. So those curves that I've introduced will be parameterized by some parameter that runs along the curves, and it's convenient in this case to use t on my time function as a parameter. So as you follow one curve among the bunch here, you find that t monotonically increases, from hypersurface to hypersurface. So you certainly have the freedom of adopting t as a parameter along the curve. So those curves have the property that ya is equal to a constant, and they're also parameterized by t. So already we have a lot of structure put in place and some amount of rigidity, and we can start working out some consequences. So for example, if I consider a displacement along a curve, I find that, of course, the coordinates will change. I forgot to introduce one more thing, which is that there will be a tangent vector to all of those curves. So this congruence will have a tangent vector field. The tangent vector field, you'll think I'm abusing the letter t here. I'm using it for everything, but I'll just call the tangent vector t. So the congruence of curves have this property. It's parameterized by t, and the tangent vector is T alpha. So the meaning of T alpha is that if I consider a displacement along the curve, the displacement would be along the tangent direction, and the increment in coordinates is going to be related to the increment in parameter. In this way, this is just saying that T alpha is just dx alpha over dt as I move along the curve. Another way of looking at this is to say that as I consider a displacement along the curve, the change in t will be given by dt, which will be given by, well, its partial derivative along, as I change the coordinates, times the coordinate displacement. So that would be true for any displacement, but if I consider a displacement along the curve, dx alpha is expressed in this way. And if dt is to be equal to dt, I have an equation linking the gradient of the time function with the tangent vector field T alpha. And that's what I wanted to work out. So one mathematical consequence of the construction is that we already have a linking equation between our tangent vector and the gradient of the time function. That has to be identically 1. All right. So that's a useful relation we'll use a little bit later. What I've done so far by introducing this construction is to construct an alternative coordinate system that I can use instead of the original one, which is x alpha. So we had the original coordinate system x alpha, and of course, at the end of the day, I want to retain complete freedom in setting up this coordinate system, but the construction gives me an alternative, and the alternative is given by the time function and the spatial coordinates ya. Because it's obvious that those coordinates are good coordinates in my domain here, because if I select ya, that means that I've selected one of those curves. If I select t along the curve, I've selected basically a crossing with a given hypersurface. So I can locate myself in my domain by either selecting these coordinates, these parameters, or selecting these coordinates. So in either case, I have a good coordinate system. And in general, there will be some relationship, that may or may not be simple, between the original coordinate system and the alternative set. So in general, there will be some relation where x alpha can be, in principle, be expressed in terms of the alternative coordinates. There will be some formal relationship between the old coordinates and the new coordinates. If I wanted, I would have the freedom of getting rid of the old coordinates and deal only with the new coordinates, and that would be equivalent to saying that, well, this relationship is actually the identity relationship between the new coordinates and the old coordinates. I have the freedom to do that. But I also have the freedom of retaining the full, arbitrary original coordinate system. All right. We have parametric relations that describe the curves. If we find out, if we write down this relationship between the old coordinates and the new coordinates, because the new coordinates are really, built upon the construction and the congruence of curves that goes in it, what we really have here is a system of parametric relations for the curves gamma. Because what those equations say is that, well, if ya are treated as parameters and I vary t, I'm picking a curve and I'm moving along the curve. And that equation would describe the displacement along the curve. But I can do it the other way, which we've done before. We can say, well, let's keep t fixed and let's vary ya. And doing that, I'm basically constructing displacements on each hypersurface. So basically, all of this is built into this into those equations. So it's the usual thing where we have, once we're given a congruence, we also automatically are given a bunch of cross curves. We've seen that before, and now it just so happens that the cross curves are all going to be contained within each hypersurface. So it's the same sort of construction that we've seen many times before. if I pick those relations and I construct partial derivatives, for example, if I take a partial derivative with t and I keep ya fixed, well, I get a very specific displacement where I keep ya fixed means that I keep the curve fixed. I move along the curve. I move along t. And that, by definition, as we called it before, is the tangent vector field to my flow of curves. So my tangent vector field I can basically define by I can calculate by taking partial derivatives of those parametric relations with respect to t. The key here is that we're keeping ya fixed. That means that I'm moving along one of those curves instead of moving across curves. If I take partial derivatives with respect to ya, keeping t fixed, as I just said, that corresponds to displacements within each hypersurface. And that is also the definition we've seen many times before for the tangent vector fields along each hypersurface. So this is the tangent to the congruence. And these are the tangent vectors to sigma t. So little by little, all of this is coming together very nicely. And we're going to use all of this to, I guess, to just keep firming this up. One consequence of those relations is that the vectors that I just introduced here are Lie transported along each other. And that's also something we've encountered before. That's essentially the statement that second partial derivatives will agree. And if you just unravel the notation, you find that, well, this requirement that second partial derivatives must agree is the statement that these vectors will be Lie transported along the congruence of curves. And of course, I could say the same thing. So T alpha is going to be Lie transported along each one of the tangent vectors on the hypersurfaces. So that's a useful property that we'll also use in our further developments. Okay. I've talked about the normal vector before. So I'm going to plot it somewhere around here. So the normal vector would point in this way. And the normal vector, of course, we know how to define it. It's defined in terms of the gradient of the time function. But the thing to recognize is that n will not agree with t. The n vector will not agree with the t vector. That's my requirement that, or that's my, the absence of a condition that says that those curves have to be orthogonal to the hypersurfaces. So if they are orthogonal, of course, that means that we've aligned n and t, and we do have the freedom to do that, but it would be a restriction of the total freedom we have. In general, I will say that, well, there's no reason to assume for n to be aligned with t. So this vector over here will not be in agreement with t, and there will be a relationship basically between all of these things. So let me just rewrite this equation, but now I'll insert the proportionality constant. N is going to be minus some normalization factor. It's not a constant, it's a function. And n is going to be a very important quantity in everything we're going to be doing. It's called the lapse function. And we'll see this more clearly in a moment, but it's really a measure of how much proper distance there is between one hypersurface and the next. Because n, n is a normalized vector, so it can be thought of as a four velocity going up along each one of those curves. dt would be an increment in coordinate distance between those two hypersurfaces, and n is going to be the thing that converts an increment in t into a proper time increment. That's something we'll see more clearly in a moment. But the lapse function is very important, and it carries useful information about the foliation that we're constructing here. It's really a way of defining n or specifying n would be putting a lot of rigidity into the construction. So that's one important definition that we'll put in. And the other statement here is that, well, the other statement, of course, is that n is going to be orthogonal to all the tangent vectors on each hypersurface. So that's something we have, and that's something we'll be using. And the other thing that I want to do is to just repeat what I said before. I want to introduce a decomposition of T in terms of a basis of vectors that I get when I join n and the tangent vectors. So by having the tangent vectors on a hypersurface and having the normal to the hypersurface, I have a very good vector basis that I can use everywhere. And I can decompose any vector or any tensor in terms of that basis. And here I just want to decompose T in that basis. And I'll just write it down. T is going to have a component along the normal direction, but it's also going to have components along the tangential directions if T is not aligned with n. And A, it's also something very important. It's called the shift vector. So just to draw a picture here, so if I draw one of my hypersurfaces like that, and if I draw one of my curves, so it's going under, it's crossing the hypersurface, and it's going right here. So the tangent vector is going to be going up this way, tangent to the curve. The normal vector is going to be going, where do I want it to go? It's going to go like this. And, so T will have a component along n, and T will have a component tangentially to the hypersurface like that. So it's really a breakdown of T into the fundamental directions that are given by n and NA. The n that occurs here is the same n that appeared here. That's something I need to justify, because it's not obvious that the normal component of T necessarily would have to agree with the lapse function as defined here. But it turns out, and that's a quick calculation, that this n has to be the same n as here because of this relation right here. So we can check that very quickly. So if I were to do something more general, if I were to say that T is decomposed into some normal component plus some tangential component, I could go and check that that this relation, has to be compatible with the first equation we had on the board. So I can multiply through by grad T, and of course the result has to be equal to 1. Otherwise, I would have an inconsistency. Now, doing this means grad T is minus 1 over n times n. And what is T? Well, T is A times n alpha plus the rest of it. And that multiplies minus 1 over n times n alpha. And, n times n is minus 1, so I kill this minus 1. That's why I had it in the to begin with. And I get A over n, and that's equal to 1 only if A is equal to n. So basically, n can be defined either in this way, as I did, or it can be defined as the normal component of the flow vector in the basis n E alpha. So that's a neat way, because that's how you basically define the shift and the lapse in the same place. You can define it like this and then verify that this is compatible with that. All right? Okay, so basically all I'm doing right now is to flesh out the mathematics of the foliation. I can do a few more things before going back to the Hamiltonian business. So we're going to play this game here that, we're going to retain the full covariance of the formalism by, insisting that all the equations can be written in terms of the original coordinate system and be fully covariant in that coordinate system. But we also play the game that, we also have at our disposal, given the foliation, given the congruence, we also have at our disposal an alternative coordinate system. And the beauty of this coordinate system is that, well, it's really tied to the construction. Everything will look simple in that coordinate system because it's all tied very neatly with the construction that we started with. So what I want to do now is to just write down a few things as if I were, that apply if I decide to use t and ya as a coordinate system in my space-time. So, for example, what would be the metric in that coordinate system? That's really the next question I want to consider. So, what is the metric? I'm not going to write here. So the metric in this coordinate system, well, we just need to construct it. So first of all, we're going to look at coordinate increments. And here I'm still using the old coordinate systems. And, well, I can express those, this full differential in terms of partial differentials. And I can use those, vectors up here as a substitute for the partial differentials. So basically, what I'm trying to do here is to decompose a coordinate displacement in terms of a component along the curve and a component across curves or a component along the hypersurface. So that's just a mathematical identity because these vectors here have been defined in terms of those partial derivatives. So there's nothing surprising here. The other thing I can do at this stage is to break this down in terms of normal and tangential components. I can just plug this in into this equation. So T alpha can be expressed as n alpha plus the shift, and times the shift, and I multiply this by dt, and then I have the next term. And I can basically, separate the normal from the tangential component. So I have n dt in the direction of the normal vector. And I have E alpha A plus NA dt, sorry. That's not what I wanted to say. I have NA dt plus dya in the direction of the tangential vectors. And I can use that to calculate the metric, to calculate ds squared. So I get g alpha beta that multiplies two of these things. I have n dt n alpha plus, well, what I had before, dya plus na dt times e alpha a. And then I have another copy of this, but I have to change the indices. So I have n dt d n beta plus dyb plus nb dt that multiplies e beta b. And I multiply it through, but that's going to be easy because there will be no cross terms because those vectors are tangential, this vector is normal, and the cross terms will all go away. So what do we get in the end? We get n dt that multiplies n dt times minus 1. So we get minus n squared dt squared. And then we get g alpha beta that will multiply e alpha a, e beta b. And that we recognize as being the definition for the induced metric on the hypersurface. That's going to give us our h ab. And that multiplies dya plus na dt times dyb plus nb dt. And by just doing this little calculation, we have a nice expression for the metric in terms of the new coordinate systems. This will be the, this will be part of the TT component of a metric. There's going to be another part arising from here. this will be the spatial part of the metric. And we also have time spatial, multiplying these guys and these guys. We also have mixed components to the metric. They can all be read off from this expression. HAB is equal, by definition, to the projection of the spacetime metric onto each hypersurface. So that is the usual famous 3+1 decomposition of the metric. Right, and there, that's an equation that tells you a bit more precisely what the meaning of the lapse and shift would be. For example, if you follow, follow a displacement along a curve, YA is equal to a constant. So for displacement along gamma, dya is equal to 0 because that's how we define our curves. For those displacements, ds squared is equal to minus n squared dt squared. So we get rid of these guys, but we pick up these guys over here, also multiplying dt squared. So basically, an increment in proper time is going to be related to a coordinate displacement in t. There's a minus sign here in this way. So the relationship between an increment in proper time and an increment in t as you go up the curves involves this factor right here, and the lapse function is basically involved in that, but the shift vector is involved as well. If you make the vectors, if you make the curves orthogonal to the hypersurfaces, then of course the cross terms will disappear, and n in that case will be the translating factor between the increment in proper time and the increment in coordinate time. But in more general situations, it's n squared minus the square of the shift that enters that relationship. Right? Another special case is that if you consider displacements purely along a hypersurface, in which case dt squared would be 0. So you put that equal to 0, you put that equal to 0, and you end up with the statement that the coordinate, the space-time interval on a hypersurface is related to that metric over here. So that's the same definition for the induced metric that we used before. And then in general you have mixed terms because you have this non-orthogonality property between the curves and the stacking of hypersurfaces. All right. Any questions about this? Yep. Which one?
The dt squared.
That would be basically a problem with the foliation. So that would be a pathology that would occur, for example, if the curves would become null or if the hypersurface itself would become null. No, so mostly it would be a problem of the curve becoming null. We would find that an increment along the curve would produce a 0 interval. So in practice it doesn't, well, so long as you insist that the curves are time-like, then the construction guarantees that you will not run into that problem. Okay, other questions? Okay, so the point here is that, again, we're playing this dual thing. So so if we keep on using the original coordinates, then the metric is whatever metric we have in this coordinate system. If we, rely on the construction and choose to take advantage of those alternative coordinates, then the metric will take this more specific form. And when we go and construct a Hamiltonian, we will basically rely and take advantage of the construction and take advantage of those coordinate systems. A side consequence of this that I'll just write down, but I won't derive here, is the statement that if you're given that metric, the full metric determinant is going to be a product of the shift, the lapse function times the determinant of the spatial metric. So basically, you just take this metric, you arrange it in nice matrix form, you calculate the determinant, and you work it out and that's the result that you get. So I give you a proof in the book, but it's a pretty straightforward thing. Okay. So now I think I have enough here to start talking about doing the Hamiltonian formulation for a field theory. We have enough structure in our 3+1 decomposition that we can do all of these things in a nice, geometrical, meaningful way. So I'll go back over here. All right, so let's do the Hamiltonian of a field theory. In curved spacetime. So we know this. That's given to us. That's the starting point, as we saw before. If we want to get a Hamiltonian from all of this, we have to do something analogous to what we were doing over here in flat space-time. We have to define a canonical momentum that's going to be given in terms of those time derivatives of the field. But now we have to decide what are we going to mean by the time derivative of our field. Before I told you that we would mean the time derivative, the normal derivative. We would associate the time derivative of the field with the normal derivative. We could do that. We don't have to do that. There's an alternative choice, would be to define the time derivative of the field to be, instead of being the normal derivative, it could just be the derivative along the congruent. Those are not the same thing. So either I go along the flow or I go along the normal, but the flow is not aligned with the normal. So I have to make a decision. If I align the flow, of course, I don't have to make a decision, but I don't want to align the flow, so I have to make a decision. And the decision I'm going to make here is that we're going to follow the flow. So the congruence is going to be the thing along which we calculate time derivatives, and I'm going to define the time derivative of a scalar field to just be the derivative along t, not along n. So I was lying to you before. You'll forgive me, of course. So that's what I'm going to do. And in fact, I want to do this not just for a scalar field. I want to do this in a way that would generalize to vector and tensor fields. So instead of saying that we're going to say that it's the partial derivative along t, we're going to say it's the Lie derivative along t. And by doing that, we're going to have a definition that holds for all types of tensor fields. So, the declaration, the first declaration here, the first choice that we make is to say that what we used to mean by the time derivative of a field is going to become the Lie derivative of our field along the flow lines, that is, along the vector t alpha. So dt psi will generalize to what I'll call, well, I might as well call psi dot. And psi dot, by definition, is going to be the Lie derivative of our scalar field along t. If we are dealing with a scalar field, of course, there's no distinction between the Lie derivative and a partial derivative. But if we were dealing with a vector field theory, or later on, as when we do this for gravity, we'll take it very seriously that we mean a Lie derivative. So this is the derivative along t, not n. And just a second, let me finish the thought. So I have a lot of freedom in the construction. I can always choose after the fact to align t with n, in which case I can choose to make this a derivative along the normal directions on a hypersurface. I have the freedom to do that. The point is that I don't want to restrict my freedom. I want to have a complete freedom. And that's why I introduce a flow t in addition to a normal vector n. You had a question? Right. Yeah. So the point is not to give up on the freedom, not to put in too much rigidity. We just want enough, not too much. And the way to achieve this is really to dissociate the normal direction from the direction of the flow. We can realign them whenever we want. We have the freedom to do that, but we have the freedom to do something else sometimes, and sometimes it's more convenient. In fact, it's very convenient to retain the full freedom. So that's our starting point. And now we have to make a definition for the canonical momentum. And here, it's going to look a little bit strange. The canonical momentum, I'll call it pi, is going to be defined to be the partial derivative with respect to psi dot, as defined here, not of the Lagrangian density. We're going to absorb the square root of the metric inside the Lagrangian density and put that in our definition of pi. And the first observation is where in the Lagrangian formulation we were insisting that this should be a proper scalar. By throwing in a factor of the determinant of the metric here, we're saying that, well, this is not going to be a scalar. This is still a scalar, right? It's defined as, as a Lie derivative. This is a proper tensorial operation. This is a proper scalar. So everything here is a scalar except for root g, and the root g is preventing this from being a scalar. So this is not a scalar. It's called a scalar density in somewhat older terminology. The point to remember is that this is not a scalar. Why is that? I was asking me that when I was first, going through this material, trying to put that into my course notes that eventually became the book. And I tried very hard to, well, I thought initially that this was just an idiosyncrasy of the old literature, that people just, were used at one time to deal with scalar densities, and they felt it was sort of convenient to continue to do that at the level of the Hamiltonian. And I tried very hard to convert everything into scalar quantities, and I failed. It just, wouldn't work for me. I mean, there's something that just goes wrong. I don't know why it goes wrong. I never, sorted it out, but I tried and tried. I never made it to work. It seems that the Hamiltonian formulation really wants you to deal with densities, not scalars. So maybe one day you'll tell me why. I've been asking my students ever since, and no one has told me why yet. I'm sure there's some deep reasons for this. Maybe it can be made to work. It's just that it's clumsy and inconvenient to do it. Anyway, we're just going to live with it. We're just going to admit that our Hamiltonian quantities are not going to be scalar quantities. They're going to be either scalar densities or vector densities or tensor densities, depending on whether we're dealing with scalar fields or vector fields or tensor fields. All right. So now we have our canonical momentum. So this is the canonical momentum. If we do this for a scalar field, of course, it makes no difference whether the root g is here or whether it's outside the derivative. When we do it for gravity, of course, it will matter a lot. So, and it's important that it's inside the derivative in that case. So we keep it here. Okay. The next step is to construct a Hamiltonian. At this stage, it's pretty straightforward. We just follow the analogous things. So the Hamiltonian density in this case is just going to be pi times psi dot. And it's understood that we re-express everything in terms of pi when we do this, minus the Lagrangian density. But of course, we have to remember to throw in the root g, because we've done it here. We have to keep doing it over here. So the Hamiltonian density, again, is not a scalar quantity like the Lagrangian was. It's what's called a scalar density because of this extra factor of root g. Well, that's the definition for the Hamiltonian density. And the full Hamiltonian is going to be the integral of this. That's curly h over d3y. And here I don't throw in a factor of root h because it's already contained here. So the full Hamiltonian is just a straightforward integration of the Hamiltonian density over the coordinate volume element. At this stage, this is okay. So at this stage, we have a proper scalar quantity. Well, we have, in fact, we have a function. We have a number. So, but it has, it has the virtue of being, after integration, the dependence on the coordinates, of course, disappears. So that's the full Hamiltonian. Yep.
How this works exactly, because the root g is equal to n root h. So I can see that the root h comes out. We seem to have an extra factor of n.
Yep, and we keep.
Okay.
Yep. Yep. So n, when we're at the level of integrating over the spatial coordinates, n appears as if it's a scalar function. So it behaves as a scalar on the coordinate transformation. So the extra factor of n doesn't spoil the, sorry. I guess I'm not addressing the point you're addressing.
It seems that it changes what we mean by the total energy on a space-like surface.
It could. There would be a danger of doing this. But in fact, so one thing I wasn't planning to do, but something I do in the book is to go through all of this for an example of a scalar field. And in fact, what you find when you construct a Hamiltonian density is that it, so when you look at this, so this is relatable to an energy density as measured by somebody. The point is, which somebody are you picking? And the person you're following, the person who's making the measurement, is actually the person that follows the flow.
So at the end is the factor which corresponds to the different observers who can measure the.
That's right. That's right. Yeah. So the dependence on the lapse and shift basically will tell you how how the energy density depends on the choice of observers. So it's built in. Yeah. But that's the weird thing with Hamiltonian formulation is that all the stuff that we thought we didn't want in GR, all the beautiful general covariance, we sort of throw by the we don't lose it entirely because it's still built in, but it's not manifest anymore. It's not explicit. It's lost. It's somewhat lost. It's not visible anymore. And now we have to live with those extra things that are really coordinate freedoms. Really, I mean, the choice of a lapse and the choice of a shift is really a choice of a flow. It's really a choice of a coordinate system. So we retain that freedom of redefining the flow, redefining the coordinate systems attached to the flow. So we still have that coordinate freedom built in, but now it's expressed in a very different way, and it's not expressed in a straightforward way like we are used to in terms of scalar quantities and general covariance and all of this. It's really the freedom of changing what you want for n, changing what you want for NA, and because of that, it's it's a bit more hidden and implicit compared to what we had before. Other questions? Okay, so I think what you see here is that, well, we've sort of imported the essential ideas from the flat space-time construction, but we've made it more compatible and more palatable from a geometrical point of view. But we do have a Hamiltonian formulation for our scalar field theory that really relies on this whole construction. First relies on the stacking of hypersurfaces, the foliation, and then it relies on having made a choice for congruence that gives us a choice for the coordinate system. We can change these things. We can change the foliation. We can change the congruence. All of that freedom is still there. But at the level of writing equations, at the level of getting a number for these things, those quantities will reflect the choice that we've made. And that's a bit unusual and perhaps a bit uncomfortable in GR. And we're going to have to see why this is useful as we keep going. At the level of a scalar field theory, of course, to get the Hamiltonian, if you're going to do quantum field theory in curved space-time, well, to get this Hamiltonian formulation would be a starting point. You would start writing down commutation relations between the field variable and the canonical momentum. You would build that into your Hamiltonian. You would construct a Schrödinger type equation for that construction. the Schrödinger equation would be basically the usual sort of thing where you would have a time evolution for your wave function, but it would be a time evolution attached to the flow. So all of this can be done in curved space-time the same way that it can be done in, a Schrödinger formulation of a field theory in flat space-time. It's not the way it's normally done. It's not the way that you typically learn it, but you can do quantum field theory in a Schrödinger picture by looking at what's known as a functional Schrödinger equation for your quantum field. All of this can be done. All of this can be generalized to curved space-time using this formalism. So probably the main reason why all of this was done in gravity was to have a starting point for a quantum formulation of GR. And I think all the variants that we've seen over the years, including loop quantum gravity and these things, all go back to that in some way. I mean, it's been disguised heavily since then. The choice of configuration variables has been refined. People have considered all sorts of better ways of defining canonical variables in the theory, but all of this is basically a variation on the original theme, which was proceed along those ways and try to quantize it to get a quantum theory. I'm not going to pursue this, of course. The main purpose for me, as I told you, was that after we get our Hamiltonian for GR, we're going to have a way of getting a definition for total energy, total momentum, total angular momentum for our space-time. And that is what I'm after here. That's really my angle for doing all of this. Okay, so we have a few more minutes before lunch. So let me just go into some of the steps that will be required in GR. And well, basically what we're going to be thinking about here is doing all of this for GR. So what will be standing in for our scalar field is going to be the metric. What's going to be standing in for the dot will be still the Lie derivative. We're going to have a canonical momentum associated with the metric, and so on and so forth. But of course, I'm going to have to be careful with what I mean by metric. When we're talking at the level of a Hamiltonian formulation, the Hamiltonian density, or the Hamiltonian itself, is really a functional of the field configuration on a single hypersurface, right? So you can think of this Hamiltonian as being a functional of the field configuration on one slice and its canonical momentum on that slice. So the Hamiltonian is really something that lives on one of those hypersurfaces. The same is going to be true in GR. When we're talking about the field configuration in GR on one hypersurface, we're really talking about the induced metric, HAB. HAB will be our configuration variable for GR, and the canonical momentum associated with that is going to be something that also lives on a hypersurface. This will be our pair of conjugate variables for the Hamiltonian formulation of GR. So we're going to come back to that, a little bit later. To get the Hamiltonian in GR from the action principle, of course, we have to go back to the actual Lagrangian density. A major complication in GR is that we know that our action principle in GR involves not just a bulk term, but also a spatial term, a boundary term. Life would be very nice and simple if you could just ignore the boundary term in this whole business, but you cannot. So most of the work that we're going to have to do starting now and through the afternoon is going to be to keep track of what's going on the boundary. It's not going to be hard. It's just that we're going to have to keep very careful. We're going to have a very careful bookkeeping of everything so that we don't lose track of anything. And there's going to be lots of stuff that needs to go in just to have the accounting of what's going on at the boundary. But the boundary is key. Turns out at the end, and that's why we spend so much time on the boundary is absolutely key, because if you look at the Hamiltonian, it's going to have a bulk term and a surface term. The bulk term vanishes if you have a solution to the field equations. The whole Hamiltonian is a boundary Hamiltonian on solutions. So the way that people say it is that if you evaluate the Hamiltonian on shell, which is an awful expression that particle physicists use when they say that they do it for a solution to the classical field equations, when it's on shell, the Hamiltonian is a pure boundary term. And that boundary term tells us everything about the total energy, total momentum, total angular momentum of the spacetime. So it'll get some time. It'll take some time to get there. We'll have to be very, very careful about working with the boundary. But we have to be if we want to extract all the bonanza of information that's contained in the boundary Hamiltonian. So let me just get started so that we can proceed this afternoon. Okay, so just to remember, so now we're doing the Hamiltonian formulation of GR. And just to recall, the action, the gravitational action, I won't bother with the matter term this time. The gravitational part of the action involved a volume integral of the four-dimensional Ricci tensor. So I'll put a 4 here just to be explicit. And we had this boundary term that involved the epsilon. It involved the extrinsic curvature of the boundary embedded in space-time. It involved the metric determinant, and it involved, an integration over the boundary. So that was the starting point, and as I told you, we have to, we have to keep careful track of that boundary term. So the region of space-time I want to look into will have this following shape. I'm going to bound it with 2 of those hypersurfaces. So it's going to be bounded by an initial surface of constant time and a final surface of constant time, time meaning the time function we've talked about. So there's going to be a cap bounding it in the future. There's going to be a cap bounding it in the past. And there's going to be a spatial boundary that's going to bound it spatially. So that's going to be, I call it sigma 1. That's going to be sigma 2, 2 of those foliation hypersurfaces, and the cylinder around it, which is really a 3-dimensional, closed surface, that I'm going to call B. And inside of this, of course, I have a whole stack of those hypersurfaces. I would have another one over here. I'll do it in dash. I would have a generic, hypersurface sigma t in there somewhere. So what we imagine here is that, well, we have this volume, V, inside here, this 4-dimensional volume, and that volume, of course, is foliated into a stack of hypersurfaces sigma t, and, well, that's basically just what I had before, but now I have an explicit boundary that bounds it. And the boundary is formed by sigma 1, sigma 2, and the rim around it, B. So I can say that the boundary here, that we have to deal with is going to be the rim B. It's going to be sigma 1, and it's going to be sigma 2, all joined together. We have that V is foliated by sigma t. But all those hypersurfaces now are bounded, right? So they also have their own boundaries. So this hypersurface is going to have a boundary st, which is going to be a closed 2-dimensional surface. This one over here will have, S1 as its boundary. This one up here will have S2 as its boundary. So V is foliated by sigma t. Sigma t is bounded by St. And the rim itself is foliated by St. B is foliated by this stack of ST closed surfaces. In V, I have coordinates x alpha, which may or may not be chosen to be t and ya. On sigma t, I have coordinates ya. On the boundary, I'll have another set of intrinsic coordinates that it's a two-dimensional closed surface, and I'll call them theta a. Theta a are intrinsic coordinates on ST. And on B, I'll have another coordinate system which may or not be related to T and sigma A and theta A. So you see where dealing with the boundary starts becoming convoluted, because sigma T is basically our starting point. We have a stack of sigma T's inside our boundary. Sigma T is going to be embedded in space-time. And we know all about describing the embedding of that hypersurface in space-time, and we're going to be talking about the induced metric on sigma T, its extrinsic curvature, and all of that. B is also a hypersurface embedded in space-time, and if we're going to be dealing with the boundary, dV, we have to deal with B as an embedded surface in space-time. So B itself will have its own induced metric, will have its own set of intrinsic coordinates, will have its own extrinsic curvature. We're going to be dealing with ST. ST is an embedded surface in sigma T. So now we do the embedding one dimension down. Sigma T is embedded in four-dimensional space-time. It's a three-surface. ST is a two-dimensional surface embedded in sigma T. So we repeat the whole game now with the induced metric on ST and its extrinsic curvature, but now we go from 3 to 2 dimensions. Well, if we can do it from 4 to 3, we can do it from 3 to 2. There's really no obstacle. But we have to do it because ST has to be dealt with if I'm going to be foliating B with those. So we have to do the embedding of ST within sigma T, but I could think of ST as being embedded in space-time as well. So we could think of doing the embedding directly in space-time and saying that we're dealing here with a two-dimensional surface embedded in a four-dimensional space-time. Well, we have to do all of that. So we're going to be introducing a legion of induced metrics, a legion of extrinsic curvature, and we're going to have to keep track of all of these things when we actually write down what we mean by something so simple as that. And the point again is this. When I consider the boundary integral here, I really consider a boundary, part of the boundary integral is going to come from sigma 2, and this will involve its extrinsic curvature. It will involve another thing for sigma 1, which will involve its own extrinsic curvature. We will have the extrinsic curvature of B, which is different from all the other ones. But more than that, we're going to want to express everything in terms of a foliation. So B will be foliated into a bunch of closed two surfaces in the same way that V is being foliated in a bunch of closed, bounded three-dimensional surfaces. So it's the bookkeeping of all of this that's going to keep us busy this afternoon. I think the ideas are not strange. The ideas are very familiar from what we've done previously in the course. We've done all of those embeddings. We have considered those extrinsic curvatures before. There's nothing new or surprising here. What's going to keep us busy, as I said, is make sure that we have all the bookkeeping that we need and do it properly, systematically, so that we don't lose track of what we're doing. So it takes quite a bit of an effort to rewrite all of this into a form where we have the ability to extract the canonical momentum and construct a Hamiltonian density. It takes a lot of effort just to put it in the right shape, to put it in the right form. And the right form is basically where everything here is expressed in terms of foliated quantities. So we'll have a lot of fun this afternoon dealing with that. I think I'll break here so that we can start directly from here this afternoon. Any questions before we break? Yep.
Would it be easier to just have a smooth surface and not have to deal with the sigma 1 and sigma 2 and just have one big integration and maybe deal with, I mean, you'll have the problem that it'll go from space length to time length. But other than that, you have a whole lot less bookkeeping to do.
I don't think you can get away from the bookkeeping if you want to keep the foliation.
Okay.
So it's really the foliation that requires all of this. So to make this smooth would not buy you very much, because you want to really shape all of this in a way that fits with the foliation. And it's really that requirement that requires all of this. You had a question? Somebody did.
I was just looking at the parameters for the B surface. Here.
Yep.
It's 3 components. Is it?
Yep. Yep.
And okay, I guess that's it. Well, yeah, that surface isn't along T necessarily. It's not purely along T. Like the projection of I onto the I don't even know what I'm saying.
Well, it looks more mysterious than it is, because in the end, at the beginning, I'm going to say, okay, we can choose the intrinsic coordinates of B to be arbitrary. But it would be kind of stupid to do this when we've already introduced perfectly good coordinates here, right? So Zi will turn out to be the union of T going up on the boundary and sigma A, sorry, the theta A's that go around. So basically, I'm going to take theta A and T to be what I mean by the coordinate Zi. But I don't want to make this commitment right away. I want to keep the coordinates free or independent for the time being. So basically, the coordinates on B are going to be the time coordinate that moves upward, and whatever coordinates I set up on each one of those closed boundary surfaces.
So each of those surfaces, sigma, those are all going to be orthogonal to T.
No, well, I'm not sure what orthogonal to T means.
You said that. Are they the same ones as those ones?
Yeah. So while the sigmas are exactly the same ones.
Okay.
So
they're
those
not
are the surfaces of our foliation.
Yeah.
It's just that here I drew them straight as opposed to to more flat. So those sigmas are exactly the ones we had before. The only thing that I've added on top of this is the bounding surface around it. So I'm bounding it, for example, with I'm bounding it up here. So I'm putting a wall here, I'm putting a wall there, and that's my B. But of course it goes around, so it wraps around. Okay? Okay, so we'll see how this plays out when we come back in the afternoon.